Welcome back. Today we're going to continue what we started in the last video on shear and moment diagrams. So we're going to practice them a little bit more, review what we did last time, and in particular I want to make sure we do some examples that involve distributed loadings. So a quick reminder of what we're doing with shear force and moment diagrams. If I have a beam, let's say it's a cantilevered beam, and it has a distributed loading somewhere on it. So say maybe right here in the middle of the beam, it has a distributed loading W of X. Usually a great idea to start with a free body diagram. And on our free body diagram, at the wall, maybe let's call this point A, we would have a force in the Y direction potentially, a force in the X direction, and a moment at point A because it's a fixed support. And acting in the middle of the beam somewhere, we also have our distributed loading that acts downward. And those are the only loads on this beam. Use your equilibrium equation, solve for those reactions. You would find that AY has to be exactly equal to the area under this distributed loading curve. That's the only downward force on it. AX would actually equal 0. And that moment would come out to be counterclockwise because it has to balance the fact that this distributed load is going to cause a clockwise moment about point A. Now, the problem is usually going to ask us something like find the maximum shear force and the maximum bending moment. And we could come along anywhere we want and cut open our beam and draw another free body diagram where we find the internal loads, the internal bending moment and internal shear force. Then we could come along to another place on the beam, take another cut, find the internal loads, and we could cut right here in the middle of our distributed loading and find the internal load, and maybe cut one more spot out there on the end. And after finding all those locations, we could plot them on a shear force diagram. And we could plot the blue point and the green point and the orange point and the red point and keep going until we had an entire curve. But I strongly encourage you to think about using the graphical method we talked about last time because it helps us get it faster. So what you would do in this case is at the very left end, the first thing that happens to the beam is you have an upward point load of AY. So we're going to start our shear force diagram right up here at AY. And then we have a section of the beam where the distributed load has a magnitude of 0. Remember, the distributed load tells you the slope of the shear curve. So since there's no distributed load, this has no slope, and no slope looks like that. So we would actually have, if we took cuts at the blue location and we found the internal shear force there, it would actually equal AY. And the same thing with the green location, the internal shear force would also equal AY. But now is where things get interesting. We reach the part of the beam that has a distributed load on it. So remember, the distributed load tells you the slope. Since it's a downward distributed load of W, our shear diagram is going to have a downward slope of W. And how far you drop from here to here is going to be exactly equal to the area under this curve. Well, when I did my original free body diagram, I would have found that AY is also exactly equal to the area under that curve. So for this simple beam, we're going to end up right at 0 when we get to the end. And if you wanted to know the shear force at that orange location, you could go and find it. Now we reach the point where there is no distributed load for the rest of the beam. There are, in fact, no loads for the rest of the beam. So this has to be 0, and it's going to stay 0 for the rest of the beam. And there is our shear force diagram. Just sketched using the fact that we know that point loads are going to cause upward jumps and distributed loads are going to cause a downward constant slope equal to W, and we have to end at 0 at the end of the beam. So if we want to find Vmax, guess where it is? It's anywhere in that first section of the beam, and the Vmax is equal to AY. Moment diagram is always a little bit harder, but once you've drawn the shear diagram, that is the next thing to do. One of the hardest parts of moment diagrams is often figuring out where to start, especially when you have a fixed support and a reaction moment at the beginning. My guess is that I'm going to start at MA, but the question is, will I start up here at plus MA or down here at minus MA? The answer is we are going to start down at minus MA, and I can explain a few reasons why. The first is I know that at the end of the beam, since there is no couple moment, I have to end at 0. So out here, we're going to be at 0. I also know that the slope of the moment curve is given by the V curve, and since the V curve is positive everywhere, I'm going to have uphill slopes all the way along the beam. I have to end at 0. In order for you to have a increasing moment and end at 0, you got to start at a negative location. If we start up here and then all the slope is positive, we're going to end up way high up here, not at 0. So there's one of the reasons we have to start down here and go upward. Another way you can reason out why the moment diagram is largely going to be negative is look at the direction the beam is going to actually bend. The beam is going to bend downward, which means we're going to end up in kind of a concave down shape. That is indicative of having a negative bending moment. A positive bending moment tends to lead to positive curvature. Negative bending moments lead to negative curvature. Finally, do you remember when we were doing internal loads of a beam and we took a cut and we could draw either the left side of the cut or the right side of the cut? Our sign convention always looked like this for V, up over here on the right side and it's down over here on the left side. And for our bending moment, a positive bending moment was this way. Counterclockwise on a left face and clockwise. Do you remember what happens with an upward point load? It tends to make the shear force when we're drawing it from left to right go upward. So when you're drawing from left to right, I want you to think of this side of a cut. So this is always going to give us kind of an upward jump. Similarly, using the same side of the cut, a clockwise moment on this face is considered a positive bending moment. So if I have a clockwise moment ever applied to a beam somewhere, what it's going to do is cause my bending moment diagram to jump up. So anytime I have a clockwise bending moment, my bending moment diagram will jump up. Anytime I have an upward force, my shear force diagram will jump up. Well, what direction is our original reaction moment? It is counterclockwise. So a counterclockwise actually causes you to jump down. Beginning of your diagram, you have to jump down because it is a counterclockwise moment. Okay, let's sketch the diagram now that we know where it's supposed to start. Well, we're going to begin now with a positive upward slope of AY, constant positive upward slope of AY. Slope here is AY because that's how big your V diagram is. And so if you wanted to find the blue location, you just come straight down here and it would be right there on the curve. It will have a negative bending moment, but it will be slightly smaller in magnitude than where we started because we're coming uphill. And the same thing with the green location. Now, right when we reach the beginning of this distributed loading is when our moment diagram will no longer be a straight line because now we have the slope of the moment diagram starts at AY, but it's going to decrease and stay positive. So what that means is we have a slope of AY right here, but by the end of that distributed load, we need to have a slope of 0. So using slope of 0 as our guide right there, we need a parabola that looks kind of like that. And then from here on out, the rest of the beam, we should be at 0. I know these curves don't always look that great. Sometimes I have to redraw them several times to get my parabola to show what I'm trying to show. But the point is that right here, the slope is AY just like it was before. Right here, the slope is 0. And in between, it is a parabola that is concave down. The shear diagram is positive is why this is increasing. And because the shear diagram has a negative slope, it becomes concave down because these are related by a derivative. And if you wanted to know the moment at the orange location, you could come down here and find the actual moment on that curve. So we have sketched out our curves. This is straight, followed by a concave down parabola. And the important thing is if you wanted to know this point right here where the parabola starts, you would use the area under the V curve to figure out how much M changes from there to there. It's got to go up by the amount of this area. And then from here to the end, it's got to go the rest of the way up by the amount of the area under the triangle. So we can use the area under this rectangle followed by the area under this triangle to figure out exactly where this transition point is going to happen. You want to say this distance right here is equal to area 1. The rest of the distance right here is going to be that blue area 2. And if you've done everything right, those areas should take you from minus MA right back up to 0. I want to just write down those calculus equations again to remind you what we're doing. dV dx is equal to minus W of x. What that means is that the slope of the V curve is equal to the magnitude of W. Also, we have the dm dx, also called the slope of the M curve, is equal to V of x, which is the magnitude of your V curve. We can also do the integral direction. If I wanted to know the change in v between any 2 points, I find the integral from point 1 to 2 of minus w of x, which is telling you that the change in v between any 2 points you care about is always going to be the area under w curve, and the change in moment between any 2 points is going to be the integral from 1 to 2 of v of x. So the change in m is equal to the area under the v curve. And that's what I just showed you. If we find that pink area, that tells us how much m changes going from point 1 to point 2. If I find that blue area, that tells you how much m changes going from point 2 to point 3. And to figure out how much the v dropped from here to here, I found the area under the w curve. So you can use both the areas to figure out step changes or decreases or increases. You can also use the magnitude w to figure out that this slope is w. You can use the magnitude ay to figure out the slope is ay. You can use the fact that this is going down to figure out that your slope is going to go from ay down to 0. So it's got to be concave down. There's our recap from yesterday. Let's practice with 2 examples using distributed loads. Here's my first example. A couple of distributed loads, both 800 pounds per foot. We always need to start with a whole free body diagram because I need to find the reactions at A because they will impact my shear force and bending moment diagram. We have a rectangle. At point A, we're going to have reaction forces, AX, AY, and a moment at point A. Draw it counterclockwise or clockwise, whichever way you want. I'm going to replace my distributed loads with equivalent point loads. So that's using the area underneath that loading curve. It'll be 800 pounds per foot times, looks like it acts over 8 feet, which gives me a grand total of 6,400 pounds. And the other one on the bottom looks just like it. Also going to be 6,400 pounds in the other direction. We can sum forces in the x direction really quickly. We get that ax equals 0, and if we sum forces in the y direction, we've got ay upward, 6,400 pounds downward, 6,400 pounds upward. Ay will also equal 0. Finally, we'll need to sum moments to figure out ma. So summing moments about point A has to be 0. I will have in a positive direction ma. Also in a positive direction, I'll have the 6,400 pounds down here on the bottom, which is causing a counterclockwise moment, and the distance away would be 8 feet plus another 4 feet gets me to the middle of the rectangle, so times 12 feet. And then my negative 6,400 pounds, because the other 6,400 pounds is going to cause a clockwise moment, and its distance away would be half of 8 feet or 4 feet. And those have to all sum to 0. MA is going to come out to be minus 51,200, and the units will be pound feet. The negative means I drew it in the wrong direction on my free body diagram. Instead of acting counterclockwise, MA is going to be 51,200 pound feet clockwise. That direction is going to matter when we go to figure out if it's going to be a positive or negative on our bending moment diagram. Now that we have that, we can start drawing our shear force and bending moment diagrams. Start with shear force. To begin our shear force diagram, we start at 0, and then we go in and we look and see if there are any reaction forces on the left end or any point forces. There is. There's AY. If AY acts upward, we're going to jump upward. If AY acts downward, we're going to jump downward. AY happens to be equal to 0, so we get to stay right at 0. And the next thing that happens is we have immediately a distributed load that is pushing down on the beam. So we need to start out going downhill with a constant slope. What will the slope be? You can find out the slope by looking at how big W is. The slope is going to be downhill 800 pounds per foot. If you want to call that negative, you can, but it's clear from the figure that you're going downhill. Now, do we want to figure out how far we end up at when we get to the bottom? Well, we can also find that from our distributed load. We just need to find the area underneath the curve. Call it area 1. Area 1 is going to be, it's a rectangle. The height is 800 pounds per foot, and the distance it acts over is 8 feet. So we did that math already. That is 6,400 pounds. So we are going to end up at minus 6,400 pounds on our shear force diagram. Now what happens at the middle of the beam? All of a sudden the distributed load acts in the opposite direction. So we got to go now uphill. There's our new slope, also 800 pounds per feet, but we're going back upwards. And if we want to figure out how much of a vertical change in V we have going from that point to that point, we would need the area under this other distributed loading. Call it area 2, and we can calculate that. It's again 800 pound per foot times 8 feet, which is again 6,400 pounds, which makes sense. If we're down here at negative 6,400 pounds and we sure better end up at 0 at the end of our diagram, we should always start and end at 0, we better also go back up 6,400 pounds. So we used the magnitude of our distributed loads to figure out we're going downhill 800 and then we're going uphill 800. Then we use the area under them to figure out that the result of that is we end up with a 6,400 pound drop followed by a 6,400 pound rise. So we end up back at 0. And then the most important thing from this diagram is usually how big is the maximum shear in an absolute value sense. And you can see directly from the diagram, it will be 6,400 pounds. Now onto the moment diagram. We need to start with, well, we think of it as starting at 0, but then the first thing that happens to our beam on the left end is we have an applied couple moment MA. It turns out it has a magnitude of 51,200 pound-feet. And really important is it acts clockwise. Do you remember what I said about how to figure out if that means we start up here at MA or down here at MA? We're going to look at the sign convention that we have when we take this side of a cut because we're drawing our diagrams going left to right. And the sign convention is that shear forces that are upward and bending moments that are clockwise are considered positive. So that's why when we have an upward AY, we jump up, and when we have a clockwise MA, which we do, we're going to start on the plus side. I'm going to start up here with a really big bending moment of 51,200 pound-feet. Another way you could reason that you need to jump up really high to begin your bending moment diagram is to realize that our entire shear force diagram is negative, and that's going to give you an indication of the slope of this curve has got to go down, and we have to end at 0. So if you've got to go down the whole time and end at 0, you better start up high. So what's going to happen? Initially, V is 0, so we start with a slope of 0. And down here, we're going to end up somewhere here in the middle with a big negative slope, maybe right there. So we're going to end up with a parabola, something like that. So it'll actually look a little better if I move my axis down. So we start with a jump up to M, partway across. We got to have a big steep slope. So I need a parabola that starts with a 0 slope and ends with a steep downward slope. Right here, the slope is 0. Right here, the slope is minus 6,400. Then what happens? The slope is still minus 6,400, but now it's going to gradually return to 0. Still negative all the way, but at the end of the beam, we're going to have a 0 slope again. So now we're going to need another parabola that is concave up. Remember, if this is decreasing, we should have concave down. If this is increasing, we should have concave up. So it should look something like that. Now what we need to figure out is, where is this point? And we can do it by using the area under the shear curve. Let's call that area 3. It's a triangle, so we'll do 1/2. One of the sides is 6,400 pounds, and the other side is 8 feet. So if you multiply all of that out, you get 25,600 foot-pounds. So we started at 51,200. If you subtract from it 25,600, you end up at 25,600 pound-feet or feet-pounds. We've gone exactly halfway down because guess what's going to happen? Next, if we color the other triangle in green and call that area 4, 1/2 times 6,400 pounds times 8 feet, or 25,600 pound-feet or feet-pounds. We go halfway down with the first parabola, and then we go the rest of the way down with the other parabola. So we end up right back down at 0. If you have another color and want to shade this in, what's really important here? Our max moment, the absolute value of it. Max moment is 51,200 pound-feet. And we solved the whole problem. We figured out the max shear, we figured out the max moment, and we plotted them. And the important point is when you have constant distributed loads, you're going to have V with a constant slope, which means you're going to end up with parabolas in your M curve. The key thing we're looking for is, do you recognize the slopes at the interfaces and how they're going to change from 0 to very steep downward back to 0? Once you have those, you can usually get the concavity sort of right. This one switches from concave down through an inflection point to concave up. The really important thing is honestly the max bending moment. Let's do one that's a little more complicated and not so symmetric to finish out today's class. We have a beam that's supported by a pin and a roller, and it's got a couple moment on it because those make everything harder, and it's got a distributed load on it, which is the topic of the day to practice. So we were asked to draw shear force bending moment diagrams and to find Vmax and Mmax. Process is exactly the same. We are still going to start with a free body diagram of the whole thing because we need reaction forces. We have our 30 kip foot couple. We have a distributed load that I'm going to replace with a point load that's equivalent to it. We're using the area under that curve. So it's 2 kips per foot times 5 feet is what it looks like it acts over, which should be 10 kips. Then right here, we're going to have a roller. So we'll have a normal force at A, or you can call it AY. And then at point B, we've got a pin. So we're going to have BX and BY. And now we can sum forces in the X. You get that BX is 0. We can sum forces in the Y. They also have to equal 0. Downward from the distributed load, I've got 10 kips. Upwards, I've got AY, and also upwards, I've got BY. They all have to add to 0. Remember, you never include a couple in your force equation because a couple moment is caused by a pair of equal and opposite forces a distance away. So if you tried to add them, you're adding plus minus the exact same force. You should have nothing in your force equation. And then let's sum moments. Summing moments about whatever point you pick. I suggest either A or B since that's where we have unknowns. I summed moments about A in my notes. To the left of point A, I've got this downward 10 kip force. So since you're going left and then down, we're going to create a counterclockwise moment. So we'll have 10 kips, and the distance away is half of 5, 2.5 feet away. The force at A causes no moment at A because it goes through point A. Now in a clockwise direction, we've got 30 kip feet. So that'll have to be negative because it's clockwise. And then finally, BY over here is going to also cause a counterclockwise moment about point A. So that'll go in as a plus BY times, how far is B? From A, it is 10 feet away. So times 10 feet, that all has to equal 0. So we can solve for BY. Comes out to be 0.5 kips. And then going back into our force equation, we will get that AY has to be the other 9.5 kips so that they add up to 10. We did the statics part of the problem. We found all of the reaction forces. Now we can proceed to drawing our shear and bending moment diagrams. We always start at 0 and then we look to see what's happening on our free body diagram. And it looks like at that very left end, there is no point load. So we are going to start at 0, but immediately we have a downward distributed load. So that means I need my V curve to start going downhill. And it's going to keep doing that until something changes. The slope, call it 2 kips per foot. You can call it minus 2 kips per foot if you prefer, but it's just whatever number is sitting right here. And we're going downhill because it's pointing downward on the beam. If you want to figure out how far down you get, that is an area under the curve problem. So let's go back to find that area. If you want to call this area 1, we already found it, but it's 2 kips per foot and it acts over 5 feet. So it is a total of 10 kips. So when I get down here on my shear force diagram, I am down at minus 10 kips from the distributed load. Now what happens? Well, first of all, the distributed load stops. So from here on out, my shear force diagram is going to have horizontal slopes because I have no more distributed loading. But I also have a reaction force AY. So I need to jump up however much AY acts upward. And AY is 9.5 kips upward. I'm at negative 10. If I jump up 9.5, I will end up at minus 0.5 kips. And now we have no distributed load for the rest of the beam, so we are going to go in a perfectly horizontal line, 0 slope, until we reach our couple. Now, a couple is not a force. Just like we did not include that couple moment in our force, we don't include it on our shear diagram. So we're still at negative 0.5. Then we keep on going with our horizontal slope till we get to the end of the beam, where we have another point force, BY, that acts upward. So BY was 0.5 kips. That's really good news because that means we're going to end up right back up at 0 at the end. And there's our whole shear force diagram. the absolute value of Vmax is going to be 10 kips. Now we can go on and do the bending moment diagram. Let's figure out where we're going to start. Well, we don't have any applied couple at the left end, so we're going to start at 0. Start right there at 0, and now we're going to look at our V diagram to see what's going to happen. Well, V starts out at 0, which means this is going to have a slope of 0 at the beginning, and it's going to gradually become more and more negative. So we are heading down until over here we're going to have a slope of -10. So we need a parabola that starts with 0 slope and ends with a steep negative slope. So a nice little concave down parabola. You want to write down your slopes. Right here we have the slope is 0. Right here we have the slope equals -10, and it's concave down, so we have a parabola. Well, let's figure out how far down we would end up. Right here. Where do we find out how far down we are? We use the area of the V curve. So I want to take the area of that little triangle, call it area 2. Well, it's the area of a triangle, so we need 1/2. One of the sides is 10 kips, and the other side is 5 feet. So you multiply that out, you get half of 50, which is 25 kip feet. So we've gone from 0 all the way down to -25 kip feet based on the green triangle. Now we have this nice little stretch of the beam where we have a constant shear force of -0.5 kips. So that means we're going to have a constant slope here of something much less steep than -10. So we're going to be still going downhill with a constant slope. That slope there will be downhill 0.5 because V has a value of -0.5. We can put minuses on them. Slope of -10, slope of -0.5. Where are we going to end up when we get to this point on the curve? Well, we can figure that out by using the area under the little rectangle that goes from there to there. Area 3. Let's figure out how big it is. It's a rectangle, so its area is going to be, we have 0.5 kips times 5 feet, which is 2.5 kip feet. So we were at -25, we go down a little more, we end up with -27.5 kip feet. Now we have that giant couple moment, and it is clockwise, and it is magnitude 30 kip feet. So reminder, when you have a couple, we're always going to go back to our definition of positive bending moment on this side of a beam, and it acts like that. So if you had an upward force, you jump your shear diagram up. If you have a clockwise moment, you're going to jump your bending moment up. So we've got to jump up by 30. We're at -27.5. If we jump up by 30, we're going to end up maybe right about there. -27.5 plus 30, we're going to end up at plus 2.5 kip feet. That's from our 30 kip foot couple moment. And then what's going to happen? Oh, we've got another little rectangle. We need to calculate for area 4. What is the area? Well, it's also going to be 0.5 kips. It also acts over 5 feet. As a result, we have 2.5 kip feet that we go down, which is good because that means if we go down at a constant slope of -0.5 again, we will end up at 0, which is good. You always need to end up at 0. Your shear and moments always have to end at 0 at the end. If they don't, you have made a mistake. It's possible you made a mistake all the way back here finding the reaction forces. More likely you made a mistake calculating one of these changes. Now that we're done, we can shade in this whole diagram. What really matters on the diagram? Mmax. Can you see what the absolute value of Mmax is going to be? Right here at the bottom, 27.5 kip feet. And maybe this illustrates why it is super, super important to draw the whole diagram, because a lot of students might think, oh, it's going to be 30 kip feet because you've got a 30 kip foot applied couple. And that could be, but in this case, it's not. So you do need the entire diagram to figure out what is the max bending moment, where does it occur? And starting in the next couple of classes, we're going to learn how to then use that value to actually design the beam, figure out what kind of cross section it needs depending on what material it's made out of so that it won't break. Hopefully that helped out a little bit with these more difficult shear force and bending moment diagrams. The things that make them hard are because we have distributed loads, we are now going to have parabolas in our bending moment diagrams. All of these examples I showed had V was always negative, so these are always going downward. In this case, V was negative, so our parabolas are going downward. If my V diagram looks like this, what would my bending moment diagram need to look like then? It's going to be increasing here, decreasing there, and because we're decreasing, it's going to be concave down. So this might be a situation where I know it's going to have a peak right here, something like that. Now here, the really important thing is going to be finding that peak, that Mmax peak. And the way you're going to do that is using the area under the curve. So you would come up here and you could take the area under that V curve, and that area is going to tell you exactly how high your peak is. So that's about the only other thing that could be more difficult with distributed loads and V curves is if it actually crosses over from positive to negative, then that means your concave down curve is going to have a zero slope because V is zero, and you would need to find the max in your parabola. The other thing that was tricky about both of these problems is in this first one, we had a couple moment at the beginning because of the reaction. We had to figure out if we start up high or way down low. And one of the hints is you can always look at your V diagram, and if your V diagram's all negative, then you know you got to start high because you're going to be coming down. Versus my first kind of example is my V curve was all positive, which means you just got to start down low because your entire moment diagram is going to be coming up. This other example, we had the couple right here, somewhere in the middle of the beam, and we had to use our sign convention reminder here that anytime you've got a clockwise applied moment, you're going to be jumping up, which makes sense because our moment diagram was ending up very, very negative. In order to get back to zero, we clearly weren't going to be able to jump down and get back to zero. We needed to jump up to be able to get the curve back down to zero by the end. All right, so that wraps up my class on shear force and bending moment diagrams with distributed loads and couples. Hope you found it helpful, and we'll see you next time.